Scientists told us the moon was dead, silent, frozen in time. They were wrong. That familiar silver-white presence in your night sky has been quietly doing something that no one fully mapped until just a few weeks ago. And once you understand what it is, the way you look at it on a clear night will not be the same. Stay with me for the next few minutes. In this video, we're going to cover what scientists just discovered beneath the moon's surface, why the dark patches you can see from your own backyard on a clear night are now at the center of one of the most consequential space science stories in years, what this means for the astronauts actively preparing to go back, and the one question that space agencies are actively working through right now as mission planning continues. This is about a fundamental revision to something we thought we understood announced just weeks ago, and most people missed it entirely. If you watched the Apollo missions live, you already have a personal connection to this story, not as a casual observer of space news, as a witness. You were there when it happened. You understood what that moment meant in real time, not as archived footage, but as live television with the whole world watching. And somewhere in the way you have seen the moon ever since, it stopped being just a rock in the sky. Those astronauts left instruments behind when they came home, seismometers, precision devices designed to detect any movement in the lunar ground and send the data back to Earth. And for years after the last Apollo mission, those instruments kept recording, they kept transmitting, and what they sent back was shaking, real, measurable ground movement on a world that most people assumed was as still and silent as the photographs made it look. Scientists studied that data for years. They categorized it, debated it, and in some cases could not fully explain it. Something was happening inside the moon, something that did not match the picture of a world that was supposed to be geologically finished and quiet. That mystery sat in the scientific record for decades, and just weeks ago, a team of researchers working with the Smithsonian Institution published a study in the Planetary Science Journal that came very close to resolving it, and in doing so, opened a set of questions that are now being asked at the highest levels of space mission planning. What they found was not hidden on some obscure, distant part of the moon. It was right there in the most visible, most photographed, most commonly studied terrain on the entire lunar surface, the dark, flat plains you can see from your own backyard on any clear night. The smooth, wide patches that make up the face of the moon, as billions of people around the world have always known it. Generations of researchers had pointed to those plains as the most stable, most settled, most geologically quiet areas available, the kind of terrain that represented the obvious foundation for future human presence. The Smithsonian study says that picture was wrong. Across those smooth-looking plains, researchers have now mapped over 1,000 previously unknown crack lines and ridge formations, evidence of a moon that is compressing, fracturing, and still actively changing in ways that no prior map had captured. And this single study added 1,114 previously unmapped ridge segments, bringing the total known count on the moon to 2,634. One research team, one paper, a few weeks ago. The map we had been working from for decades just changed dramatically. The Artemis program is moving forward, astronauts are training, landing zone decisions near the moon's south pole are being made this year. This study arrived in the middle of that active preparation and adds new information that scientists say should be considered. Cole Nypaver led this research. Tom Waters, a senior scientist at the Smithsonian, was part of the team. Both have stated in published material that these findings will directly affect landing site decisions and long-term planning for human presence on the moon. That is the scientific community telling the planning community clearly and directly, the picture changed, and your decisions need to reflect it. Most people have not yet encountered the single most striking detail in this entire story, one specific fact that, once you hear it, changes your intuition about what it actually means to stand on that ground. If this kind of story matters to you, real science, real stakes, real people being sent somewhere we are still actively learning about, hit the like button right now. Subscribe so you do not miss coverage as this story continues to develop, and drop a comment below telling me where you are watching from, because viewers on this channel are following the Artemis story from across the world, and I want to know where you are in this conversation. Now let us talk about what scientists actually found, because the specifics of this discovery are more precise, more striking, and more consequential than any headline managed to capture. And what is sitting underneath those dark patches visible from your backyard on a clear night, that is where this story stops being general and starts getting serious. The dark plains on the moon have been part of human skywatching for as long as people have looked up. Long before spacecraft, before powerful telescopes, before we had any instruments at all, people noticed those smooth, dark patches against the brighter lunar surface and named them. They called them Maria, an old word for seas, because from Earth they looked like large, dark patches, almost like oceans. We have long known there is no water there. They are wide. Ancient plains of solidified volcanic rock cooled, hardened, and spread across the lunar near side in the flat, featureless expanse that makes up the moon's familiar face. And for generations of planetary scientists, those plains were the textbook example of geologically quiet terrain. Old, settled, done. Cole Nypaver, the lead researcher on this study, worked with a team using high-resolution images from NASA's Lunar Reconnaissance Orbiter, a spacecraft that has been systematically photographing the moon for years, at a level of detail that simply was not available in the Apollo era or the decades that followed. The survey was specifically designed to look for a type of surface feature called lobate scarps. You can think of these as low, so elongated ridges, the kind that form when something beneath the surface is under compressive stress, and the outer rock layer cannot hold its shape, so it buckles and folds, leaving a visible raised line running across the terrain. Not dramatic, not towering, but real, measurable, and directly meaningful in terms of what is happening beneath the surface. These features were not unknown before this study. Scientists had already identified and catalogued some of them on the moon. Tom Waters, a senior scientist at the Smithsonian Institution who has spent years studying lunar geological activity, had contributed to earlier research establishing that these compression fractures existed and that the moon was contracting. That earlier work was significant. But what had not been done, what this new study set out to accomplish, was a thorough global image-by-image survey specifically focused on those flat dark plains. Because the standing assumption was that the Maria were not where you would look for signs of active geological stress. They were the quiet parts, the stable parts. That assumption turned out to be precisely backwards. Across those dark plains, the team identified 1,114 previously unmapped ridge formations. That specific number, published directly in the Planetary Science Journal, represents something more than a count. It represents the difference between what we thought we knew and what is actually on the surface of the moon. Before this study, the known global catalogue of lobate scarps across the entire moon was substantially smaller. This single study focused on terrain that had been considered the least likely place to find signs of geological activity, nearly doubled the total. This new study showed that our earlier map was missing a very large part of the picture. That kind of discovery, one that doubles the known scope of an established geological phenomenon on a world we have been studying for more than 60 years, does not happen routinely. We have landed people on the moon. We have sent orbiters to photograph it continuously. We have built detailed global maps of its surface at high resolution, and in the middle of all of that, in the terrain most visible and most studied, over 1,000 geological features connected to active seismic behaviour were sitting unmapped. That is what makes this study worth more than a one-day headline. Tom Waters' involvement matters not just as a credential, but as context. Waters had already done foundational work showing that the moon is contracting, and that its surface is responding to that contraction with compression fractures. What the Nypaver study adds is the full global scope of that process concentrated specifically on the Maria, not scattered findings from remote corners of the moon, over 1,000 new data points spread across the terrain type that mission planners have been evaluating for human habitation. The terrain type that looks, from Earth, like the obvious safe choice. What also distinguishes these features is their geological age. Researchers can estimate the relative age of surface features by examining how they interact with surrounding terrain, whether they cut across older features, whether they show significant erosion or filling over time, whether they appear fresh or weathered in geological terms. Many of the ridges found in this study appear geologically young, not ancient remnants of a process that finished billions of years ago. Still developing features of an ongoing process, the surface is not done changing. Planes the terrain that looked smooth, and planes the terrain that looked smooth and settled from Earth. The terrain that has been central to mission planning discussions. The terrain that billions of people can see from their own backyard on a clear night, are crossed by over 1,000 crack and ridge lines that were not on any map, formed by a process that is still running. In the areas being considered for landing sites and long-duration surface presence, the scientific community does not receive information like this quietly, and this study has already entered the mission planning conversation and is expected to influence decisions being made now. There is also something that deserves to be acknowledged about the process that produced this mapping, because it reflects how science actually builds toward understanding over time. The Lunar Reconnaissance Orbiter has been in service for years, generating a continuous archive of high-resolution surface data. The data that Naipaver's team used to find these ridge formations was not brand new data collected for this specific purpose. It was data that had been available data that, in retrospect, contained the evidence for over 1,000 previously unknown geological features the entire time it was being collected. What changed was the methodology, the systematic, targeted approach to looking specifically at the Maria for compression features, the willingness to examine terrain that prior assumptions had marked as geologically uninteresting. But before that conversation can make full sense, there is something that needs to be understood about why the Moon is doing this in the first place. Because the cause of every one of those over 1,000 ridge formations is not mysterious, it is actually something you can understand in a single clear image. And that image connects everything else in this story. But here is the question nobody was asking out loud. Yet what is causing all of this? And the answer takes us somewhere most people never expected. Think of a grape left out for a few weeks. The inside dries and pulls inward. The outer skin, which cannot shrink with it, wrinkles and buckles into folds and ridges. The Moon works the same way. As its interior cools and pulls inward, the outer crust compresses and cracks. It buckles. It folds into ridges and creases because it can no longer lie flat over an interior that has pulled away from it. What was once smooth is now covered in compressed folds and grooves. The skin has not torn. It has adjusted under compression to an inside that is no longer the same size. That is the Moon. Not poetically, not loosely. As a physical description of the actual process, the Moon's interior, the deep rocky core that has been slowly losing heat since the Moon formed, is still cooling. As it cools, it contracts. It pulls inward, and the outer shell of cold, rigid rock cannot compress smoothly. It responds to the inward pull by buckling, by compressing against itself, by fracturing along lines where the stress becomes too great for the rock to hold. And those fractures, those compression lines, those places where the outer shell gave way, those are the ridges. Those are the crack formations that Col Naipaver's team just mapped in their thousands across the Moon's dark plains. This is not a new concept in planetary science. The idea that the Moon is contracting was established before this study. Tom Waters and colleagues had documented evidence of it. What this study changes is the scale of our understanding specifically, how extensively and how actively this contraction is expressed in the terrain type that has always been considered the Moon's quietest, most stable region. Here is what most people do not fully absorb when they first encounter this idea. The contraction is not over. The Moon is not a geologically completed object that went through this process in its distant past and has since settled into a permanent finished state. The cooling is ongoing. The interior is still losing heat. The outer shell is still responding. Over an enormous span of time that makes the entire history of human civilization look like a brief moment the Moon has been slowly pulling inward. And the growing network of compression ridges across its surface is the visible, measurable record of that process continuing. For most of human history, none of this was visible to us, not because it was not happening, but because we had no way to see it at the resolution it requires. The Apollo era gave us our first direct contact with the lunar surface, and the instruments the astronauts left behind gave us our first direct evidence that the Moon was seismically active in ways that were not fully understood at the time. But the connection between the contracting interior and the surface behavior between the cooling core and the shaking ground has only been coming clearly into focus in recent years. This Smithsonian study is the most complete version of that picture we have yet had. What this means, in plain terms, is something you can feel intuitively once you hold it in your mind for a moment. Those dark plains you have looked at your entire life, the same plains that made up the backdrop for the Apollo landings you watched on television, are sitting on top of a geological process that has not stopped. The surface above that process is under compression, under stress, the kind of slow, continuous stress that, when it releases, does not release gently and immediately disperse. It releases into rock that has nowhere soft to absorb it, across a world with no atmosphere to dampen the effect, on terrain that is now known to carry over 1,000 fracture lines running through it. You can go outside on any clear night and see those plains without a telescope, without any equipment at all. They are right there, the dark patches in the Moon's familiar face, visible to the naked eye. And now you know something about them that most people looking up at the same sky tonight do not yet know. That ground is not quiet. It has never been as quiet as it looked. The seismometers the Apollo astronauts left behind already told us something was happening there. The new map now tells us where, and what that map connects to what the shaking actually looks and feels like, how long it lasts. And why that duration matters so much for everything that comes next is where this story moves from geological curiosity to something that touches every decision being made about sending human beings back. There is something worth holding for a moment before we move on from this geological picture. Most of what we understand about Earth's geology was built around a planet with water, with weather, with a partially liquid mantle, with a slow churning of material that continuously recycles and resets the surface. The Moon has none of that. It is a closed system closed off, with the heat inside slowly leaking out over time. What that means is that every piece of geological stress that builds up on the Moon stays concentrated in the rock. Every crack line that forms stays sharp. Every compression fracture that opens does not fill with sediment or smooth over with weathering the way features on Earth do. The surface preserves what happens to it with a fidelity that has no equivalent on Earth. The ridges Nepeva's team mapped are not just currently forming, they are preserved records of every similar event going back across an enormous timeline, and they are still growing. There is a detail from the Apollo program that most people have never heard, and it has been sitting in the scientific record for decades waiting for exactly the kind of context this new study provides. The Apollo astronauts did not just land on the Moon, plant a flag, collect samples and leave. They set up equipment, instruments designed to keep working and keep transmitting data long after they came home. Among the most important of those instruments were seismometers, precise devices built to detect and record any movement in the lunar ground. Several Apollo missions left these instruments behind, and for years after the last crew departed, those seismometers kept picking up signals. They kept measuring the Moon, and what they measured over and over was shaking, not from meteorite impacts, not from the thermal expansion caused by the temperature swings between lunar day and night, though those were detected too and catalogued separately. What drew scientific attention was a category of event that came from the Moon's own structure, from near the surface, from the outer rock layers moving, compressing, shifting under geological stress. Scientists called these shallow moonquakes, and shallow moonquakes, it turned out, behaved in ways that did not match anything in the standard geological vocabulary built around Earth's behaviour. For decades, the source of those events was incompletely understood. The seismic data was real and extensively studied, but the surface structures most directly responsible for generating that shallow activity, the compression fault lines in the dark plains, were not yet fully mapped. The picture was missing too many pieces to be complete. The Smithsonian study, by mapping over 1,000 previously unknown ridge formations in those same plains, has now provided the missing map. The source of a significant portion of the Moon's shallow seismic activity is the same compression process that formed every one of those ridge lines. The cracking surface is the shaking source. They are the same thing, seen from two different directions. That connection matters because it means the shallow moonquake record is not a mystery anymore, and it means the areas with the highest concentration of those new ridge formations are the areas most associated with ongoing seismic events of this kind. Which brings us to the fact I have been holding back since the beginning of this video, the fact that changes the way you think about standing on that ground. On Earth, when an earthquake strikes, the experience is intense and brief. The ground moves hard and fast, the energy passes through, and within seconds to under a minute for most events, the shaking stops. That is the version of seismic activity that everyone who has ever felt an earthquake understands. It is sudden, it is powerful, and then it is over. The ground settles, the wave passes, you feel it, and it is done. Moonquakes are nothing like that. The Moon's rock is cold, dry, and rigid all the way through. Moves. The energy does not bleed out into moves. The energy does not bleed out into surrounding soft material. It reverberates. It bounces through the rock, reflects off deep boundaries, travels back up, and keeps going. The Apollo seismometers recorded moonquakes that lasted not for seconds but for minutes. And some of the shallow moonquakes, the exact kind now linked to the compression faults in those dark plains, kept shaking for more than 10 minutes without stopping. Apollo instruments confirmed some shallow moonquakes lasted over 10 minutes, far longer than a typical earthquake. Anything sitting on that surface, a structure, a joint, or a connection, would feel continuous shaking until the event ends on its own. There are no emergency crews nearby, so equipment has to be designed to handle that kind of stress. That is what the Apollo instruments recorded. That is not projected or estimated. It is measured data from seismometers that sat on the moon's surface for years and transmitted what they observed. And it is now sitting alongside a new study showing that the terrain being considered for human landing and long-term habitation has over 1,000 previously unmapped fault lines, the source of exactly this kind of event running through it. The Apollo seismometers were not asking the question of what this meant for people living on the moon. In the 1970s, that question was abstract. Apollo was a visit program, a few days, then home. The duration of surface exposure was short enough that even the seismic record, as unusual as it was, did not present an immediate engineering crisis. But we are not in the Apollo era anymore. The program preparing to go back is not planning for visits. And the question that 10 continuous minutes of ground shaking asks about the structures we intend to leave there permanently is one that has to be answered before people are on the ground rather than after. It also means something specific for structural engineering of lunar surface systems. On Earth, buildings in earthquake zones are designed using detailed estimates of how often the ground shakes in a place, how strong that shaking can be, and how long it might last. Those models are built on decades of seismic monitoring data from thousands of stations distributed across the surface. The Moon has had none of that until now. The Apollo data was foundational, but it came from a handful of instruments operating for a limited time. The combination of the new fault map from the Smithsonian study and future seismic monitoring from Artemis missions is what will eventually allow engineers to build lunar structures with the kind of risk knowledge that Earth-based structural design has always depended on. There is one more dimension to this worth a moment before we move forward. The Apollo seismometers detected different categories of moonquakes, and shallow moonquakes, the ones now linked to these compression faults, were considered among the most scientifically puzzling because of where they came from and how they behaved. Deep moonquakes originated far below the surface, somewhat predictable, tied to the gravitational pull of Earth on the Moon at regular intervals. But shallow moonquakes were different. They came from near the surface, from the geological structure itself, without any regular timing. They behaved more like quakes on Earth along active faults. Their timing is irregular and depends on how much stress is built up in the rock. That unpredictability is now a relevant engineering consideration in a way it was never required to be during the Apollo program's brief surface visits. Now here is where I need you to hold that 10-minute image in your mind, because what comes next puts real people directly on that ground. The Artemis program is not a concept being designed for the distant future. It is an active, funded program with real hardware, real training timelines, and real decisions being made right now about where to land and what to build. Astronauts are in training, mission profiles are being worked through, the engineering requirements for lunar surface systems habitats, power generation, life support, communication infrastructure are being finalized by teams whose job is to ensure that every structure placed on the Moon's surface is capable of keeping people alive under realistic conditions. The target region for Artemis surface operations is the Moon's South Pole. NASA and its international partners have been focused on this area for a combination of scientific and strategic reasons. Water ice exists in permanently shadowed craters near the poles, ice that represents a potential resource of enormous value for long-duration missions. The South Pole offers certain orbital and operational advantages, and the agency has been explicit that the South Pole is not just a landing destination, it is the foundation of a long-term presence strategy. The structures going there are designed to be the beginning of something that stays. Here is what was already known before the Smithsonian study arrived. Prior research had already identified fault zones in the Moon's South Pole region as a factor worth monitoring. Scientists had flagged it. Engineers had noted it. It was being treated as a localized concern, something specific to a particular corridor that could be accounted for with site selection care and structural design standards built around a known risk zone. Then the Smithsonian study was published, and the scope of what was known changed completely. Because the new mapping did not find that the active compression fault problem was concentrated in one corridor near the South Pole, it found that the new ridges were found spread across the Maria on the Moon's near side, not limited to one corridor. Specifically across the Maria, the flat, dark plains that are the most practical, most accessible terrain for landing and surface operations broadly. Not a narrow zone to be avoided, a terrain type. the terrain type that has been the foundation of mission planning assumptions for years. The Smithsonian study did not confirm a localized risk. It revealed that what was previously thought to be a local problem is a global characteristic of the most mission-relevant terrain on the Moon. Kolnepaver addressed this directly. In connection with this study, he stated that these findings will affect landing site decisions and long-term lunar base planning. That is not cautionary language added to a press release. That is a lead researcher describing what the data means for the field he works in. The map changed. The risk picture changed. The planning conversation has to change with it. Tom Waters put it plainly. Our findings complete a global picture of a dynamic contracting moon. A dynamic moon. Still changing. Still moving. A moon that is not a static backdrop for human operations, but an active geological environment that will continue to do what it has been doing while people are living on it. A habitat built on this terrain needs to be engineered to handle over 10 minutes of continuous shaking, including the joints between modules and the anchors for power and life support systems. That requirement did not exist clearly before this map was complete. Engineers now have to factor this kind of shaking into their designs. No one in the scientific community, not Nepava, not Waters, not anyone connected to this study, is saying that Artemis should not go. That conclusion is not supported by the data, and it is not what the researchers are arguing. What they are saying is that the surface we are planning to use is more seismically complex than the previous map showed, that the seismic events associated with that complexity last significantly longer than anything comparable on Earth, and that the planning needs to reflect this updated reality before crews are committed to the surface rather than after they are already there. There is a detail here that deserves more time than it typically gets in coverage of this story. When Kolnepaver says these findings will affect landing site decisions, he's not speaking hypothetically about a distant future planning phase. The South Pole landing zone evaluation is an active process. Sites are chosen based on slope, sunlight, resources, science targets, and geological stability. The seismic risk picture that mission planners were working with 6 months ago and the picture they are working with today are meaningfully different. That difference is not a footnote in the planning process. It is a primary input. Where people land is where people will set up equipment, where the first structures will be placed, and where the very first judgment calls about long-term habitability will be made in real time by real astronauts with real consequences. Having the correct geological picture for that decision is not optional. It is the baseline requirement for everything that follows. That is a very different conversation from panic. It is a precise, professional, scientifically grounded conversation about what is required to do this responsibly. But there is one more layer of this that the headlines mostly missed. Because this story was never just about where the first Artemis crew lands. It was always about what we are planning to build there permanently. There is a distinction that has been at the edge of this conversation since the beginning, and it deserves to be stated plainly. There is a significant difference between landing on the Moon and living on it. The Apollo missions were landings. They were historic, technically extraordinary, and deeply consequential for human civilization, but they were visits. Brief surface stays measured in hours and days, during which the exposure to geological risk was measured against a very short window of time. The astronauts arrived, worked, and came home. The Moon's surface never had to sustain them through a prolonged period of potential seismic activity. What Artemis is building toward is not that. The long-term vision behind the Artemis program, stated explicitly by NASA and its international partners, not implied or speculated, is a sustained human presence on the lunar surface, a base, structures that stay, power systems that operate continuously, habitats that are occupied not for days but for weeks and months, by rotating crews or eventually by permanent teams, the infrastructure of a permanent outpost on another world, beginning with the South Pole and designed to expand over time. Every structure in that vision will sit on the Moon's surface indefinitely. Each one will be subject to whatever the ground beneath it does, including the seismic activity now associated with the over 1,000 compression fault lines mapped across the Maria by the Smithsonian study. The 10-minute moonquake duration is not just a detail for short visits. It is a real part of the Moon's environment that long-term structures will have to be designed to withstand. Tom Waters said it in language that deserves to be read carefully. Our findings complete a global picture of a dynamic contracting Moon. The picture is now more complete, and what it shows is not a static backdrop for human activity, but an active geological environment, with ongoing processes that produce real, measurable extended ground movement. What the scientific community is specifically asking for in response to this study is updated seismic risk mapping before landing zones and base construction sites are finalized. Every one of those newly mapped ridge formations is now considered a potential source of shallow seismic events. Before crews are committed to extended surface stays, and certainly before permanent infrastructure is built, researchers are calling for a detailed understanding of which specific fault zones are most active, how frequently they generate significant events, and which areas within the South Pole target region sit closest to the highest concentrations of active compression faults. NASA has indicated that future Artemis missions will include seismic monitoring instruments, and the purpose of that monitoring is no longer primarily scientific curiosity. It is now a direct safety input. Real-time seismic data from the surface will be used to characterize the risk environment for habitation, to distinguish between areas where the ground moves rarely and briefly and areas where it moves more often and for longer. That distinction, which could not be made with confidence before the full fault map was available, is now one of the central questions of lunar base site selection. The framing that matters here, and it is the framing that Waters himself uses in describing what this study represents, is not danger. It is knowledge. Critical knowledge that arrived at exactly the right moment in the program timeline. We have this information now while Artemis is still in the preparation phase, while no crew has yet been committed to a long-duration surface stay, while the engineering standards for surface structures are still being finalized. The window to incorporate this knowledge into the planning is open. The scientists are handing it through that window as clearly as they can. That is what responsible science looks like when it intersects with a live, high-stakes engineering program. The findings are not comfortable. They do not confirm that everything is simple and the surface is as safe as the old map suggested, but they are accurate. They are verified. They are published in peer-reviewed literature by researchers with institutional credibility and years of relevant expertise, and they arrived before the decisions were locked in rather than after people were sitting on that ground. There is something else that this study implies for the broader space program beyond the immediate Artemis planning cycle, and it is worth naming even though it is rarely discussed in the coverage this story received. Multiple national space agencies, including agencies that are not partners in the Artemis program, have active lunar ambitions. China's lunar exploration program has articulated goals for robotic and eventual human presence on the moon's surface. The European Space Agency has been developing concepts for a long-term international lunar presence that goes beyond any single mission. Every one of those programs, regardless of their political relationship with NASA, is planning to use the same Maria, the same flat dark plains as their primary operational terrain. The Smithsonian study is relevant to every single one of them. A more complete seismic risk map of those plains is not a proprietary asset belonging to one program. It is a contribution to the shared knowledge base that every program planning to put people on the moon will need to consult. None of this makes the moon unsuitable for human presence. The moon is not a place we cannot go. It is a place we are only now beginning to understand at the resolution that permanent human habitation requires. The gap between what we knew 6 months ago and what we know today is a gap that needed to be closed. It has been closed. If you remember watching those first moon landings on television, you remember how it felt to see that moment. The images that came through were not sharp or vivid by any standard you would recognize today, grainy, black and white, flickering slightly. But they were live, and they were showing something that had never been shown before. A human being standing on another world, looking out at a horizon that no human eye had ever seen from that angle, and you were watching it in real time. The dark, flat plains you can see from your backyard tonight are the same plains those astronauts walked on. That is not a poetic claim. The Maria, the smooth dark terrain now known to carry over 1,000 compression fault lines, are the same type of terrain that several Apollo missions targeted and landed on. Still there, still visible, still carrying the physical record of everything it has been doing since the moment those astronauts stepped on it and came home and the world moved on to something else. For a generation of people who watched those missions as they happened, the moon is not just an astronomical object. It is a piece of lived experience. It is connected to a specific moment in time, a moment when the world did something that seemed beyond the reach of human beings and did it anyway, live on television in front of everyone. That moment does not become less meaningful when new information arrives about the geological complexity of the surface beneath the astronauts' boots. If anything, it adds a dimension that was always real but never fully visible. The scientists who made this discovery are not standing in opposition to going back. Cole Nypaver is not calling for Artemis to be delayed indefinitely. Tom Waters is not writing letters to space agencies urging them to abandon their lunar ambitions. The message from the people who did this research is the opposite of retreat. It is, now we know. Now we have a complete picture of the surface we are designing for. Now we can make the decisions about landing sites, structural standards, your seismic monitoring, habitability criteria that the incomplete picture was preventing us from making correctly. This study gives engineers and mission planners verified data they did not have before, and it arrived while decisions are still being made, not after crews are already on the ground, and the decisions ahead are significant. Updated seismic risk maps will need to be completed and integrated into site selection before crews are committed to extended surface stays. Structural standards for habitats, power systems, and life support equipment will need to account for the kind of sustained ground movement that Apollo's instruments documented. Seismic monitoring equipment on future missions will provide real-time data on which specific areas of the South Pole region are most and least seismically active. These are challenging tasks, but they are the kind of problems engineers are trained to solve. But they require the correct information, and they now have it. With the new fault map, the Apollo seismic record, and active Artemis planning all converging at the same moment, there is a question underneath it all that deserves to be asked plainly and left with the viewer to hold. We are preparing to go back to the moon. We are preparing to stay there, not just visit. We are preparing to build things that need to survive whatever the ground beneath them does, on a world whose geology we just learned is significantly more complex than we thought. A few weeks ago, with active preparation already underway, that is not a reason to stop. You go to find out what you do not yet know. You design the best mission you can with the best information available, and you build in the capacity to learn as you go, to adjust as the picture becomes clearer. That has always been how exploration works. It is how Apollo worked. It is how Artemis will need to work. What is different now, what this study changed, is that the picture is more complete today than it was 3 weeks ago. We know something real and important that we did not know before. We know where the fault lines are. We know how the seismic events associated with them behave. We know what questions to ask about which specific locations within the target zone are safest for long-duration human presence. We are better prepared today than we were before this study was published. Within living memory of people watching this video right now, we went there. We physically went. We sent human beings there and they came back, and they brought pieces of it with them. And yet, with all of that history, with all of that attention, with all of that study, the surface beneath the astronauts' boots was still keeping significant secrets. The moon is still revealing new details about itself, and in that sense, going back is not just a continuation of a program. It continues a long story of how people have tried to understand the moon, and now we're finally reaching a much deeper level of detail. The moon has been there your entire life. Familiar, constant, apparently silent and still above you on every clear night. And it turns out we are only now beginning to truly understand what it is. Not the rock in the sky that you have always known it to be, but an active, complex, still-changing world that is revealing itself to us slowly, one study at a time, exactly when we need to know. That is not a frightening thought. It is one of the most interesting things happening in science right now. The moon is not done, and neither are we. Before we close, let us lock in 3 things this video established. First, a study from the Smithsonian Institution, published in the Planetary Science Journal, has identified over 1,000 previously unmapped compression ridge formations across the moon's flat dark plains, nearly doubling the total known count of such features on the entire moon in a single piece of research. Second, those formations are geologically young, still actively forming, and directly linked to shallow seismic events that the Apollo-era instruments detected for years, events that can keep the lunar ground shaking for more than 10 continuous minutes. Third, NASA's Artemis program is actively planning human missions to the moon's south pole, and the lead researchers on this study have stated explicitly that its findings will affect landing site decisions and long-term lunar base planning. Everything in this video comes from verified published sources. The primary study referenced throughout is from researchers at the Smithsonian Institution, published in the Planetary Science Journal. Supporting information about lunar seismic activity is drawn from NASA-published research and reporting by Science Daily and phys.org. The researchers named in this video, Cole Nypaver and Tom Waters, are the actual authors and contributors to the research discussed. No claims were attributed to sources that did not make them. One important clarification on the data: The moonquake duration figures referenced in this video come from Apollo seismic records and from a separate prior NASA study on lunar seismic activity. That seismic data is directly relevant to and complementary with the Smithsonian ridge mapping study, but it is a separate body of research. Both bodies of research are peer-reviewed, publicly available, and accurately represented here. They are not the same study, and nothing in this video presents them as being the same. No speculation was presented as confirmed fact. The Artemis mission timeline was not projected beyond what is publicly documented. The geological risk was not overstated. The researchers' own framing that this is critical knowledge arriving at the right moment, not a reason to stop, was preserved and reflected throughout. This story is still developing. Mission planning decisions informed by these findings are being made in real time. The moon is not finished teaching us what it is, and this channel will follow that story as it continues. Hit subscribe and turn on notifications so you do not miss the next piece of coverage as it develops. If this video gave you something to think about, a question, a reaction, a memory of watching Apollo that this brought back to the surface, drop it in the comments below.